Hi, my name is Martins, and in this video, we'll be looking at how to use Python to solve forward kinematics problems. So to use Python to solve forward kinematic problems, we would need three libraries, particularly the SymPy for symbolic computations. Also, we're needing the NumPy for numerical computation and the plotly for the 3D interactive plotting. So that is what we'll be doing in the subsequent frames. So you will recall that we already talked about how you assign your coordinates to your joint on your robot, and we gave the example of this very robot on the screen, this robot arm. So to fill up the DH parameters, let me just explain how we came about all these values here. So we have three joints. That is this joint here, that is our base. So there's another joint here, so that's joint 2, and also we have this prismatic joint here, which is joint 3, and we have the tool tip here, which is a gripper in this case. So you will see that we already have our coordinates. This is our z0, x0 in this direction, and also y0 in this direction. Here we have z1 in this direction. Also we have x1 here, and also we have y2 and y1 here, x2 in that direction, z2 in this direction, and z3 for the approach of the tool, and also this is x3 and y3 here in the sliding direction of the tool. So for transformation, we already said that it is transformation from one joint to the other, and we can decompose that into rotation and translation. So transformation from joint 0 to 1, 1 to 2, then 2 to 3. So that's what we have here. Transformation from 0 to 1, 1 to 2, and 2 to 3. So what are the DH parameters for these transformations? So the DH parameters are the alpha, the A, the D, and also the theta in this case. So alpha is the angle that is being measured from z minus 1 to z high minus 1 to z I about your x axis. So for this one, you will see that for alpha 1, z0, if you transfer this up here, it will be taking this position where you have your x2. So, and this is z1 in this direction. Naturally, you see that it's a 90 degree in between them. However, z0 to z1, because we are moving from we are transforming from z0 to z1, so it goes in this direction, which is 90 degrees. So that's why you have 90 here. But how do we know if it's negative or positive? You will see that we already know that the robot rotation itself is in this direction. However, z0 to z1 came in this direction, z0 to z1, because if you transfer this z0 up here, it will move from this point down here. However, we are told that the robot arm actually moves in this direction, so that is why this is negative 90. So for the A1 value in this case, we know that our A is the distance from zi minus 1 to zi measured along our xi minus 1 axis. So if you look at it, the z0 here to z1, if you transfer this up, you see that there's no distance along the x axis for A1, so that's why it is 0 in this case. For D, in this case, is the distance from xi minus 1 to xi measured along the zi minus 1 axis. So if you look at this, the x0, x1, so they have perpendicular distance between them, and if you measure that distance along your z0 axis, you will see that the distance is these 3 units that you have here. So that is why this is 3 in this case. And theta, we know that theta is the angle between xi minus 1 to xi, measured about the zi minus 1 axis. So this is xi minus 1, x0, and this is x1 here. You will see that both of them fall on the same plane, so they are parallel, so there's no rotation between them. So that is why this theta 1 is 0. So from 1 to 2 now, so that will be z1 to z2. If you look at it, this is z1, this is z2, so it's going 90 degrees in this way, 90 degrees in this way. However, this joint is moving in this direction, while z1 to z2 is going in this direction. So that's why you have minus 90 as well in this case. And also ai is the distance between zi minus 1 to zi measured along xi minus 1 axis. So z2 and z1, they fall on the same joint, so that's why it's 0 in this case. So d again is distance between xi minus 1 to xi measured along zi minus 1 axis. So in this case, our xi minus 1 is x1, while the xi is x2 in this case, and you see that both of them are on the same point again, and so there's no distance between them. That's why it is 0 in this case. So for theta, angle between xi minus 1 to xi measured about our zi minus 1 axis. So in this case, that will be x1 to x2, and you see that it's a 90 degree between them. x1 here, x2 here, 90 degrees. However, when is it going to be minus or positive in this case? So it's going from x1 to x2. However, this is moving in this direction, so that's why it is negative 90. Alpha again here for the last transformation from 2 to 3, it is angle between zi minus 1 to zi. So z2 in this case to z3, you can see that they are parallel, there's no angle between them, so that's why it's 0 in this case. And also z2 and z3 also are in the same plane, so that's why a3 is equal 0, but d is the distance between xi minus 1 to xi, perpendicular distance measured along the zi minus 1 axis. So this is x2 and this is x3 here, and the distance between them is perpendicular distance between them and measured along the zi minus 1 axis, which is z2. So z2 in this axis, and that unit is L3. So that's why you have L3 in this case. For theta 3, the angle between xi minus 1 to xi measured about the zi minus 1 axis. In this case, x3 and x2, they are parallel, so there's no angle between them. So that's why this is equally 0. So when you have obtained your date parameter in this way, how do you use Python to solve this kind of problem? So that is what we want to look at. So once you open your Python in this way, so if you have Python already on your system, let me just zoom this in a bit. So if you have Python already installed on your system, probably you use Anaconda to install your Python. So you already have your SymPy. We already said that you need 3 libraries, basically your SymPy and your Plotly and your NumPy for this very work. So in this case, you import your libraries. That's the first thing you do. So I import SymPy as SP. So what I want to do is I want to use mathematical symbols. So and I want to use latex to do those mathematical symbols. So from sympy.physics.vector import init_vprinting. So init_vprinting in parentheses use _latex equals math jack, pretty_print equals false. Now all of this line, what I'm just saying is that from this library, I want to use latex for my symbols that I will be writing in this code. And also, I want to import dynamic symbols from this same library of simpy.physics.mechanics import dynamic symbols in this case. So that is what I'm doing there. I'll just run that line. So what you would be doing here is to, let me split this screen so that you can see. Let me take this back to, okay, so this is the page. So the next line here is you want to bring in your default DH parameters, which we know is the alpha, A, D, and theta, and also the symbol that I have in this particular DH parameter. In this case, I only have one symbol in this DH parameter, which is L3. So that's why I have L3, theta, which is a default DH parameter, alpha, A, and D. So, and I would say equals the dynamic symbols, which are already took in from this library. So equals dynamic symbols into L3, theta, alpha, A, D, all in this apostrophe because it becomes a string in this case. So L3, theta, alpha, A, and D. In this case, I will just be printing that here. So this is the L3, this is theta, this is alpha, this is A, this is D. So these are your default DH parameter, D, A, alpha, and theta. This L3 came from the DH parameter of the robot arm itself. That is the only symbol I have in this DH parameter. If you have other symbols in your DH parameter, you need to specify them on this line so you don't make that mistake. So after this, I would be bringing in my model for forward kinematics. If you recall, we said we have, let me open that just by this side. So if you go back to this is the forward transformation matrix model here. So this is just what I want to do in Python. I want to write this in Python. And we already said that the first three column, 1, 2, 3, are rotation, while the last column, which is the fourth column, is the translation. But in Python, the indexing starts from 0. So this is column 0, column 1, column 2, and column 3. So I'll just go back to Python. So using the same simpy library, which we took in as SP. So I want to create that matrix because at the end of the day, this becomes, I want to create this matrix in this case. So I want to create this first 3x3 matrix, this 3x3 matrix. So I'll create this column vector and also this row vector. So for the rotation, it is this first 3x3 matrix. So that's why I'm having the identifier as ROT equals sp.matrix, then in brackets because I'll be putting them in as a list. So that's why you have this kind of parenthesis, this square bracket in this case. So sp.cos theta, if you look at what we have here, okay, let me just split this also. However, it would be very small. So sp.cos in bracket theta, this symbol that we already took in, this symbol that we brought in from here, this symbol of theta. So that is sp.cos theta, which is this cos theta I, and also comma minus sine alpha cos theta. So that is minus sp.sine theta, sp.cos alpha. So the next 1, also sp dot sine theta, and also sp dot sine alpha. So sine theta, sine alpha for the third colon, also sp dot sine theta, this, and sp dot cos theta, which is this, and sp dot times sp dot cos alpha, which is this, and also minus sp dot cos theta, which is this, and multiply by sp dot sine alpha in this case. So that is that. This is 0, so that's 0, comma sp dot sine alpha. This is sine alpha, comma sp dot cos alpha, which is this. So those are the rotation components. So for this translation colon is a cos theta. That will be trans equals sp dot matrix a times sp dot cos theta, which is a cos theta. This is the symbolic representation of it in Python, and this is a times sp dot sine theta, and comma d. This is d. So we are left with this last row here. So this is the last row, equals sp dot matrix 0, 0, 0, 1, which is this line here. So at the end of the day, I want to stack all of this vertically. If you are used with Python, you know what a v stack is. So I want to stack them vertically. So I'm using m equals sp dot matrix dot v stack. So I want to stack them vertically. So sp dot matrix dot h stack, that's horizontal stack for the rotation, comma translation. So all of this are already in horizontal because we did them horizontally in this case. We did them in this way, horizontally. So because we have stacked them horizontally before, we just want to now stack them vertically now. So that is why I'm converting this previous vertical stack of the rotation and the translation in this case back into vertical from the horizontal they were initially. Then the last row, which is already vertical in this case, so just put that, and I'm printing that with this m because the identifier in this case is m. So once I run this, you will see here that this is your model for the forward kinematics. If I just open this, and let me split the screen. So if you look at this, is cos theta, this is c theta, minus also here. Okay, let me correct this. This is sine alpha cos theta. So let me correct this here. Sine alpha cos theta. Let's copy this. So sine alpha cos theta. Let me split the screen. So sine alpha cos theta, and also sine alpha sine theta, which is this, a cos theta. So this is a cos theta, a sine theta, d, and 1. So this is minus sine alpha cos theta, cos alpha, and 0. Also you have cos alpha cos theta, which is this, then sine alpha, then 0. So cos theta, sin theta, 0, 0. So that is what you have back here. So the transformation from joint 0 to joint 1, so that will come from your DH parameter. So if you look at the DH parameter here, now it's 90 for alpha, minus 90, A is 0, D is 3, then theta is 0. So transformation from 0 to 1 equals m dot subs. So I want to substitute now alpha with minus 90, which is this, A with 0, D with 3, then theta with 0. So this matrix M now, I want to make those substitutions into it. So if I run this now, you will see that if you go over what we have, you see this is from 0 to 1, from 0 to 1, and so on and so forth. So let me just use the Python in this case. So this is what you have. If you plug that into your transformation matrix, that's what you get from 0 to 1. So the same thing for 1 to 2. The alpha also is minus 90, as we can see here, is minus 90. The A is 0, D is 0, and theta is minus 90 in this case. So if you run this, you would have the A matrix for transformation from 0 to 1. So for 2 to 3, which is this, alpha is 0, A is 0, then D is L3, and theta is 0. So if you run that also, you would have this. So what is next is to multiply the transformation from 0 to 1, transformation from 1 to 2, and also transformation from 2 to 3. Multiply all of them together to get your overall transformation from 0 to 3. So if you multiply this, you get all of this. So that is the transformation in this case for all of that. So however, you can use SimPy also to simplify this expression. So if you look at it, we have trig function here, trig function here, trig function also here, but here we have trig function and also L3, 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 a constant. So how do we use SimPy to simplify this one? So we'll be simplifying them element by element, quoting their row and column. So I'm using IBB as the identifier equals sp dot matrix, that's SimPy. Then in parentheses, the overall matrix, which is I 0 to 3, which is this. This is I 0 to 3. This is the output. So in this first list, row 0 colon 0. So that is this first element. That is row 0 column 0 dot simplify, then parentheses. So it will simplify this. The same thing, row 0 colon 1. This is the element there up until this is row 0 colon 2 is this. Sorry about that. And also row 0 colon 3. However, this one has a symbol. So here it is. It's going to be a sim sp dot trig symbol simplify I 0 to 3, 0 comma 3, which is this very element dot simplify. So that is just the difference between what we have been doing before and this very line, which is this element here. This is row 0, all this row is row 0, but this is colon 3. So row 0 colon 3 on the overall transformation from 0 to 3. So because of this constant here, the same thing for this variable L3 and this constant 3. So for this very element of row 0 colon 3, it is a variable L3 in this case. So sp dot trig simp I03, which is this overall matrix. So the element I'm referencing is row 0 colon 3 dot simplify, which is this one. So that's just what you do for every other element where you have such instance. If you look at it, for all this colon 3, this is 0 3 1 3 and 2 3. So you can see for all of them you have this sp dot trig simp for 1 3, which is this, 2 3, which is this as well. So but for where you don't have that you only have 3 functions, you just use this reference the element dot simplify directly. So run this, might take a while. So this is the outcome of that. So if you look at what we have, if you want to confirm, if you check through your notes, you will see that this is the final output. This is the final output: 0 0 1 L3, 0 minus 1 0 0 1 0 0 3 0 0 0 1. And if you want to compare that to what you have here, saying, oh, are they the same? Just a quick check here. So if you look at this, where you have 3 here, if you do cos 90, if you check what cos 90 is, you will see that with that you can get out all of those variables and you'll be left with 3. So because cos 90 is 0, so once cos 90 is 0, everything you have here becomes 0 and you're left with positive 3, which is what you have here. You understand? This is just the last row that stays the same. So this is 3. So if you keep doing that, if you do this, also you have cos 90 here, so everything here will go to 0, which is the 0 you have here. So sin 90 is 1, so that's why you have cos 90 is 0 plus 1, so that will be 1 times L3 sine squared 90, which will be 1 squared. So L3, you have your L3. So if you just do the evaluation, you see that you have exactly what you have here. So for the position of the tooltip, we said what you have on the last column, which is this column now, is your position. So this is the position on the x-axis, on y-axis for the tooltip, and this is the position on the z-axis. So just to reference that, so px equals ibb row 0 comma colon 3, which is this. So if you run that, you will see that that will give you these very values. So this is the position of the tool in x-axis. Also for y-axis, that will be 1 comma 3, because this is row 1 colon 3, this is row 2 colon 3. So that's for z. So 2 colon 3, that's for z. So that is what you have here. So that is the tooltip position in x, in y, and on z axis. So that is what you have there. Okay, so there is another example of such system. So this is the DH parameter of a certain robot arm. So transformation from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5 in this case. So this is twist, link length, joint offset, and the joint angle. So you have the symbols you have here: D2, D4, theta 1, theta 3, and theta 5. Those are the symbols you have in this DH parameter. Pi over 2 is 90. So if you, the same code would work. So the libraries are the same. So once you run that, so in this case, my symbol in the DH parameter are the theta 1, theta 3, theta 5, D2 and D4. So theta, alpha, A and D are the default DH parameters. So once I run that, so theta 1, 3 and 5, D4, D2 are the symbols in the DH parameter table that we have here: D2, D4, theta 1, theta 3 and theta 5. So that is why we have them here like so. So the same transformation matrix for the forward kinematics, which is this. So in this case, transformation from 0 to 1. So if you just go back to what we have here, so theta is 0, sorry, alpha is 0 here. So I'm substituting all of this into the matrix for forward transformation. A is 0, D is 0, then theta is theta 1 in this case. So if you run that, this is the outcome for substituting all of this into the model for the forward transformation, forward kinematics. Also for the second transformation from 1 to 2. So we see from 1 to 2, alpha is 90, pi over 2 is 90, A is 0, D is D2, and theta is 0 in this case. So if you run this also, you get this out. And here also you have for 2 to 3, alpha is 90, A is 0, D is 0, and theta is 3, theta 3 in this case. So if you run this also, you have your output. Then from 3 to 4, alpha is 0, A is 0, and D is D4, and theta is 0. If you run this as well. Then from 4 to 5, alpha is 0, A is 0, D is 0, and theta is theta 5. So you have that. So the overall transformation is for you to multiply transformation from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5 all together, which we just do with this expression in Python, and get out our outcome, which is this in this case. So let me just open this. So that is what we have. So also we can use the method to simplify like we did. Let me just minimize this. So the same method to simplify. So after doing that, we just get a more simplified output. In this case, it might take a while because it's quite large. So here is the simplified model of that. So we can also determine the position of the 2 points in X. So that's for Px, for Py, and for Pz. And also we can use the same pi to just know how the profile of the two tips would go, using this for X position, Y and Z position. So Fx equals Sp dot lambdify into the symbols you have in the DH parameter, which is D2, D4, theta 1, theta 3, theta 5, comma Px. The same thing for your Py and for your Pz alongside the numpy. So I'm using here the matplotlib, import matplotlib in this case, and import numpy as np. And I'm using this line to convert my degree to radian, because Python will evaluate your degrees, your angles in radians. So I'm converting my degree value into radians in this case. So if you run this, we just run to import those libraries and bring this library in. So we have three variables in theta. So we want to know the angles that our tooltip can go through. So theta's 1, 3, and 5 equals np dot lean space. The lean space is a function in MATLAB. Sorry, you call it lean space in MATLAB. So, but here we are using it in Python. So np dot lean space. So degree to radian from 0 to degree to radian to 360. So lean space will give us, we generate numbers from 0 to 360. So for theta's 1, 2, and 3. So here I'm just using ZX, ZY, and ZZ for the tooltip position using the np.array or fx, fy, fz from 15 units to 15 units just for this experimentation. So theta's 1 to 3, 3 and 5. So this is just my plot codes. So here I'm saying I want to have a subplot of only one axis, ax1. So on the same ax1, I'm plotting 1, 2, 3 plots, and I'm setting my x label as this, my y label as this, my legend should be at a default location, and I'm putting my grid using my plt.grid. So that might take a while. So here is the profile for my tooltip in x, in y, and z axis. So angles from 0 to 360 and the tooltip position in mm. So we can see the profile. This is the legend px, py, pz, and this is how the position will vary for the tooltip with this forward transformation matrix that we have done for the forward kinematics of this certain robot arm. So in this video, we have looked at how you use Python to solve forward kinematics problem. In subsequent videos, we'll look at how to use Python to solve inverse kinematic problem. So you can use the same code for other forward kinematics problem. I will leave the link for the code used in this video in the description. Thank you very much.